Let me give you a short overview of my research. So, of course, with this, I'm going to try to touch on 4 topics. So first of all, I'm going to try to give you an overview of basically all of my research, except for 3 topics, which I'm going to handpick and be a bit more precise about. So one of them is combining baryonic acoustic oscillations with Big Bang nuclear synthesis. One of them is on Cannibalistic Meta, and one of them is on spectral distortions of the CMB. Now, since I'm like super excited about all of these topics, I'm probably not going to have enough time to cover all of them in super much detail, which is why hopefully we'll go through the first part here about what is my research in general quite quickly. Then I will take a bit more time for the other chapters. Okay, so to give a short overview of my research, basically there are different parts of my research that I'm going to draw on now. So one of them, for example, would be numerical optimizations. So there's like using neural networks for skipping certain calculations in our Boltzmann solving code. So this is linear Boltzmann equations that we skip by using a neural network. The results of this are kind of nice. So on the left-hand side, you see the function that we want to predict. Next to it, the neural network prediction. They look almost the same. You can see in the middle or on the right-hand side, there's like this difference of this function that we want to predict, which is called ST0. And the residual is like 3 orders of magnitude smaller than the function itself. So that seems kind of nice. Correspondingly, the CMB that we reproduce is also really close to what we want. And currently we're working on extending this to different parameters. So we started with just a couple of lambda CDM parameters, like the meta over density, baryon over density, H0, and so forth, and so on and so forth. But now we're extending it to also include like curvature, neutrinos, and whatever else you want, fancy and effective. Okay, so you can see here the agreement is quite okay. So if you have more questions about any of these topics, just ask me afterwards, and I'll be happy to go back to slides or tell you more detail about them. So this is one part of my research. Another part is actually talking about angular power spectra, which might be relatively relevant to this group. So I picked this also as well, where I basically, together with Zalda Jaga and Simonovic, developed like an algorithm to compute the angular power spectra beyond the limbo approximation. And we actually abandoned this kind of traditional approach where you integrate the perturbations over a line of sight. And instead, we reorganize the integrals into 2 parts. One is like a cosmology-dependent part. One is a cosmology-independent, purely geometric part. And if you pre-calculate the geometric part, all of these calculations are much faster. So you usually gain orders of magnitude in the calculation of these very simple angular power spectra. So this is just a simple thing. Here, for example, I show the linear prediction for the angular power spectrum versus the limber prediction, and you can see that at low wave numbers L, this has quite the discrepancy. So red versus black curve. And similar thing, if you include nonlinear corrections and massive neutrinos, then you also see that the green and the blue curve also disagree quite a lot at low scales. And this is what this program is basically for. So how well does it work? Well, quite fantastically, actually. So the error is less than a per mil. So this should be for the next surveys quite okay, quite enough. So for example, in the pessimistic Euclid range, this would be perfectly covered. So what actually is also nice about this is that this can include all relativistic effects. So if you just have galaxy clustering, like in this case, that's fine. But you can also include all other effects. So for example, the lensing of the galaxies, some GR effects which arise due to like the distortion of the volume due to the gravitational potentials, and redshift space distortions, of course, and all of the kind of different effects, Doppler effect, you name it, you can include, and you get kind of a very nice total galaxy clustering curve, which is also predicted to around 0.1%, which is super high precision. So this could be basically used to calculate the angular power spectrum until L of like, let's say 100, 500 or so, 1000, and then the rest you can still do with the limbo approximation because that large wave modes L, the limbo approximation is anyway very accurate. So this, of course, also works for bin asymmetric correlations. So where you have two bins which are separated by some redshift and you correlate them, though then the error, of course, gets slightly higher. There's also some slightly higher error when you talk about lensing. Okay, so this was my second topic. Then I also worked a bit on just using certain likelihoods and doing some analyses based on this. So for example, I'm in a collaboration with a group in CA Saclay, and they've kindly provided us like the Flux power spectra for a bunch of their simulations. And we built a likelihood on top of this, which basically uses some Taylor approximation of the Flux power spectrum in the basis of cosmological parameters, which means that we can do some predictions of how the Lime alpha forest depends on the cosmological parameters. So this would be the big red contour, while the blue contour is just Planck alone. And then we have some intercombinations. The green is Lime alpha plus Planck, and the orange is Lime alpha plus Planck plus lensing plus some preliminary BAO data. And you can see that basically the Lime alpha contour puts some independent constraints on the neutrino mass, which are not very competitive. But if you combine them with the Planck constraints itself, you actually force it to be slightly more constraining on the neutrino mass, because the region where the neutrino mass is in agreement with the value of NS, so the scalar tilt is actually only towards smaller neutrino masses. So the overlap is actually at smaller neutrino masses and relatively consistent NS value. Okay, what we however noticed and what we're still investigating and what we're going to continue investigating is that there's a huge discrepancy actually between the Lime alpha data and the Planck 2018 data in their prediction of the meta fraction omega m. So Planck, you know, has like 0.31 or so as a meta fraction. Lime alpha data predicted something like 0.28 or so. And actually, if you really get into it, a lot of other probes of the late large-scale structure actually also probe values of omega m which are slightly below 0.3. So in this sense, there could also be this kind of omega m tension. And finally, if you now use the sigma 8 value from the Lime alpha data, which is very much compatible, as you see on the left-hand side with Planck, and you combine it with this much lower omega m value, you actually get that Lime alpha data is much more compatible with weak lensing data. And this is just purely an effect due to this smallness of the omega m meta fraction. So in the future, we're going to test this again with an emulator likelihood, and we're going to also extend it to analysis for DC Lime alpha data. So this is ongoing right now. Okay, so this is part of my Lime alpha analysis. Then we have a paper about multi-integrating dark matter. Since I don't want to spend too much time on it, I'm going to make this very quick. So you could imagine that dark matter interacts with photons, baryons, or dark radiation, and correspondingly you can derive some constraints depending on how your cross-section scales with temperature. So here are, for example, 3 plots of dark matter interacting with baryons and the corresponding exclusion regions in a log-log space of the mass of the dark matter particle versus cross-section for 3 different scalings with the energy of the dark matter, or temperature of the dark matter to be more precise, which is NB equals 0, NB equal -2, and NB equal -4. And you can see that you get different corresponding exclusion regions on the cross-section. Okay. However, you can, of course, also look at what happens if you combine multiple interactions. And so what we found, what I think is most interesting about this paper, is that if you combine photon and dark radiation interactions at the same time, you can simultaneously solve or you can simultaneously ease at least 2 tensions, which is the S8 clustering tension and the H0 tension. And this basically works by letting one of the interactions, the dark matter dark radiation interaction, allow you to go towards higher H0 values, and the dark matter photon interaction and allowing you to go to smaller S8 values by suppressing the power spectrum. And this then allows you in total to get slightly closer to where you want to be with a very high H0 value and a very low S8 value, depending on whether you think that you should go there. Okay, we also showed that dark matter baryon interaction does basically nothing to this plot. So you can see the left and right hand plots are almost identical, like the difference is super tiny. And so dark matter baryon interactions do not seem to be a very good extension of this, do not seem to solve this very well. And yeah, this was our result. Okay, let's now get actually into the stuff that I'm a bit more passionate about, which is my 3 topics of choice to present. So first one will be baryon acoustic oscillations and Big Bang nuclear synthesis. For this, I want to quickly give you first an overview of why this is interesting. So we have baryon acoustic oscillation plus BBN measurements of the Hubble constant. So if you combine them, you can actually measure the Hubble parameter, which is the expansion rate today. And this actually turns out to be relatively close to the Planck value and relatively far away from the value determined by the local distance ladder by Rees et al. You can even be more general and phrase it as like you can compare all the different H0 measurements that have been recently released. And honestly, there's quite a lot of them, and more are coming. And you can see that there's a couple of different positions that these measurements can be in. So a lot of them are predicting very high values of around 73, 74. Some of them are predicting intermediate values of around 70. And a lot of them are predicting these kind of low values of 67 or so. And now the question is, which of these is right, or are they all right? And what is interesting about this combination of baryon acoustic oscillation and Big Bang nuclear synthesis is that it's not using any perturbation theory. So it's basically, except for the worth of the fluctuations leading to baryon acoustic oscillations, but otherwise the BAO itself is, of course, a geometrical probe. Okay, and this means that you kind of have these very nice geometric or background probes that are independent of these kind of cosmic anisotropies of the CMB. So how do we do it? Well, the idea is basically to combine BBN and BAO. So let me give you a quick summary of BBN. It's basically Big Bang nuclear synthesis, how primordial elements such as helium, hydrogen, and lithium, deuterium, and so on were created through the primordial plasma. And this basically depends on how quickly the reactions that generate these elements, like the photo dissociation of the elements compared to their recombination, happens compared to the timescale of variation in the early universe, which is basically the Hubble parameter in the early universe. The Hubble parameter in the early universe varies strongly with the number of effective degrees of radiation species in the early universe, as well as depending highly on how many baryons you have. And so from the helium abundance, you actually get a very strong very strong constraint on the effective number of ultra-relativistic degrees of freedom in the early universe. And from the deuterium abundance, you get some strong constraint on the baryon abundance. And so there's some other things to be said about some other properties. So for example, the helium-3, which you could theoretically also use, sadly depends a lot on stellar evolution. So it's quite hard to measure. And lithium-7 is something that you could theoretically measure, but it's still very much in tension, and we have no idea why this is. So this kind of says that our BBN models are still somewhat incomplete. However, if we take the BBN measurements of only deuterium and helium at face value, then we get these kind of 2 constraints. I plot them here in a parameter space where I have the baryon fraction on the bottom, and on the left I have the number of ultra-relativistic degrees of freedom in the early universe, or the number of neutrino-like species, and its deviation from 3, or the lambda CDM prediction. And you can see that if I combine both measurements, I get a quite precise measurement of both quantities. Why do I need those? So I get omega B and an effective. Why do I need those? Well, I can look at the sound horizon that is measured by the Bayesian acoustic oscillations, and I see that having measured these, I basically get a very precise measurement of the sound speed, because the sound speed depends on the Bayesian photon ratio, the loading basically, and this depends on the Bayesian fraction and the temperature of the CMB. The latter is well measured. Similarly, the Hubble expansion parameter at early times depends on the temperature of the CMB, of course, radiative species, then a lot on the number of effective degrees of freedom, so effective neutrino species. So that is quite well predicted by BBN as well. And finally, on the omega m. But the omega m, we can use the BAO to constrain. So we use the BAO calibrated in a sound horizon up to variations of omega m, and then we will use the BAO itself to constrain omega m. How do we do that? Well, first let's talk a bit about BAO, but I don't need to be very thorough on this because I guess you're all more or less experts on BAO already. So it's the increased clustering on the scale of the sound horizon, which you can see either in the transverse or in the radial distance. So either with the angular separation delta theta or with the redshift separation delta z, which corresponds to different relations. So you always have this kind of fixed scale of Rs. And in the one case, you divide it by the angular diameter distance. In the other case, you multiply it by the Hubble parameter. So the degree of freedom of this kind of BAO measurement is always that you have this kind of fixed sound horizon from the early universe, and then you view it with either the angular diameter distance or the Hubble parameter. Okay, sorry, let me skip this slide. So at low redshift, what you actually see is that the degeneracy direction, both of them, the Hubble parameter and 1 over the angular diameter distance, they're both basically proportional to h naught and only very, very weakly depend on this omega m parameter. While at high redshift, the dependence on the omega m parameter is much stronger, and it is actually 2 different degeneracy directions that you get. So in total, when you look at the galaxies at low redshift, you get a very broad contour because we saw that it varies a lot with omega m. You only have this partial calibration and so on and so forth. But you have a certain degeneracy direction, which is going to be different for low redshift and high redshift Bayesian acoustic oscillations, because there's different dependence on the angular diameter distance and Hubble parameter on omega m and h naught. So for the low redshift galaxies, you get this kind of blue contour, which is basically the data release 12 of SDSS. And you also get from the data release 14, which is kind of a new data release, also the EBOS quasars, which basically use the high redshift clustering. So the clustering measured from the light of the quasars using the Lyman alpha forest techniques. And you get quite different degeneracy contours. And now you can ask yourself, where do these overlap? And the combined contour actually turns out to be smack dab down there, where also Planck is. And the orange contour here is the reset-I measurement. So you're quite close to Planck and a bit far away from reset-I. Now, what is to be said about this is that, of course, both the galaxies and the Lyman alpha contours here are individually perfectly fine with reset-I value, only if you trust both of them, and that is, of course, an assumption that you have to make, that you trust both of these measurements perfectly, then you get this red contour, which is then in disagreement with the reset-I measurement. So you could now say that either of these 2 measurements has to be wrong, or there's a discrepancy between this local probe and the late probe through BAO plus BBN. Okay. Now you can also extend this by including also an effective. So the change is basically just blowing up contours, because your BBN measurement of the sound horizon gets a bit more uncertain due to this inclusion of the N effective. But since BBN measures is quite well, there's not a huge uncertainty added. So this is even like invariant for simple models of dark radiation that already persisted in the early universe, generating some ineffective. Well, you can see, for example, that Planck blows up a lot more than this BAO plus BBN probe. Okay. Next one would be cannibalistic dark matter. And cannibalistic dark matter is a really fun model. Let me try to explain it to you step by step. So the most important feature, or the most interesting feature of this cannibalistic dark matter, will be this intermediate cannibalistic phase. So if you have warm dark matter, for example, it behaves at very early time where the temperature is much bigger than the mass, like radiation. And later, when the temperature is much smaller than the mass, it behaves basically like cold dark matter. That is warm dark matter summarized. However, now we have this interesting cannibalistic dark matter, which has some intermediate regime, the so-called cannibalistic regime. We will see in a second why it's called like that, where basically the co-moving density, rho times scale factor cubed, is proportional to 1 over the log of the scale factor. So it doesn't go like radiation, 1 over A. It doesn't go like cold dark matter, which is constant, but it has this kind of weird logarithmic dependence. So it goes down, but slowly. And this is kind of a feature that you can use to kind of bridge the gap between warm dark matter and the CMB. And we're going to see why in a second. First, let's discuss why you get this cannibalistic phase at all. So this is a tale of basically 3 interactions. You have the 2-to-2 interactions, where you have 2 cannibal dark matter particles going in, 2 cannibal dark matter particles going out. There's nothing really happening with the temperature or the masses of, or the mass conservation on either side. So this we simply assume to be very efficient throughout to simplify our calculations. But then the next 2 interactions are the ones that are important. So we assume that this cannibal dark matter fluid is not one which obeys to some Z2 symmetry or something. So it can actually violate number count conservation. So for example, we have this upper, or this middle diagram, I should rather say, where we have 2 particles coming in and 3 particles coming out. So actually the temperature of the 2 particles coming in has to be quite high. There's a lot of energy in these particles, and it's being used up to generate the mass energy of the 3rd particle. So the 3 particles on the right-hand side, they have to have lower kinetic energies. They have lower temperature, basically. So this means that this process here eats up temperature or kinetic energy and spits out mass energy instead. However, you can already imagine that if you do not have enough temperature, if you do not have enough kinetic energy, you do not cross the threshold for generating the 3rd particle. So this means that this process is inevitably becoming very inefficient as the temperature decreases too much. So if you have a very small temperature, you cannot do this process anymore. And there's another process, which is the inverse process, which could still happen. Because what it does, it takes 3 particles and it eats them up and spits out only 2 particles. So in this case, you take the mass energy of the 3rd particle and you basically convert it into thermal energy for the other 2 particles. And so now you can imagine this kind of tribe of cannibals where there are 3 cannibals on a boat and they are freezing in the North Pole. And now they're thinking, oh, how can we increase our temperature, our core temperature? It's dropping too low. So they start to eat up one of their friends, and only 2 of them remain, but the 2 are now warmed up with the nice meat in their stomach. So this is kind of why it gets this strange name, cannibal dark matter. So you use the mass of one particle to generate temperature. So you gain temperature, but you lose mass. So this can still happen at any point because you always have mass energy. There's nothing preventing this from happening, except that maybe the interaction cross-section of 3 particles hitting each other can become much smaller than the Hubble expansion rate. And then this kind of is a classical freeze out of a reaction. So the first one we assume to be very efficient throughout, just for simplifying our calculations. The second one, we say it becomes inefficient as the temperature becomes smaller than the mass. And the third one freezes out at a point which we can basically set by just setting the interaction rate of this fluid. So if we make it super interacting, of course, this process is never going to freeze out. Okay. So what we actually did in the paper was we did a very effective parametrization depending on a couple of assumptions. So you can see here the number density conservation and energy density conservation equations. Energy density conservation looks basically the same as it always does, but the number density conservation is not actually conserved there's this kind of term which tells you how much does the number density change, which is of course kind of what you expect, right? If there's this process of 3 particles going to 2 particles, you change the number density. And it must be proportional, of course, to the interaction rate, which is this gamma 0. Also, you need 3 particles coming in, so that's why it's proportional to n cubed. And then there's a bit of about chemistry. So there's some chemical potential in there. So this mu parameter here will be the chemical potential, while T is the temperature. Okay, so this efficient 2-to-2 scattering we actually only do to get a nice form of our background distribution, such that we can assume it to be in kinetic equilibrium, which enforces either Fermi-Dirac or Bose-Einstein distribution, and also to kill like higher orders of perturbation theory, where we would otherwise have to think about anisotropic shear or higher order Boltzmann equation moments or whatever. But we don't really care, so we just restrict it to be overdensity and velocity, basically. So we restrict it to be like a classical fluid. So the second assumption is completely decoupled from the Reming thermal bath. So there's no interaction where you just have dark matter, cannibal dark matter annihilating into standard model. This would be much more complicated to think about because you would have like a lot more reactions. So we just drop all of this. Third assumption is the 2-to-3 scattering, sorry, there's a typo, is characterized by this gamma 0 interaction rate. And we also in the paper, we expanded it to be some possible temperature power law, but in the end, we found no significant dependence on this temperature power law coefficient. And of course, as usual, we assume form momentum conservation in these interactions. So what you then get is this kind of shape and forms by chemical equilibrium, namely Bose-Einstein or Fermi-Dirac, which I show the distribution function on the right-hand side. On the left-hand side, I show the evolution of the corresponding quantities guiding this distribution function. So that is one, the temperature, two, the chemical potential. The temperature is, I guess, what you can most easily interpret. So the temperature is the red curve. It goes like (8⁻⁻1), which is the scaling law of the energy of some ultra-relativistic species. It's basically like a dilution of frequency with the scale factor. And so it just goes like (8⁻⁻1). Then it gets into this very nice phase, which is the cannibalistic phase, where the 3-to-2 interaction stops because we actually drop below this magical value of T over M, so temperature over mass, being equal to 1. So that's why there's this dotted gray line in the middle at 10⁻⁻⁴. And so when we go below this magical value, suddenly this fluid turns into cannibals, and they start to eat each other up to heat themselves. So the temperature stops going as (8⁻⁻1), but instead now goes only as 1 over log A. So it kind of is being heated by this cannibalism compared to cosmic expansion. And finally, once too many particles have been eaten up and the interaction rate is thus not high enough anymore, because it scales, as you remember, with n cubed, so it needs quite a lot of particles to be efficient, then it suddenly turns very inefficient, and basically the fluid just becomes cold dark matter. So the temperature falls like (8⁻²). Okay. So what does it mean for the equation of state or the sound speed? Well, basically, it is first radiation-like with equation of state equal 1/3. Then it drops slightly to like 0.1 or 0.01. And then it becomes cold in this third phase. However, the interesting thing is in this cannibalistic regime, it is almost relativistic. So it still has a lot of the properties that, for example, warm dark matter would have. But it is not contributing super much, for example, to the CMB or the fluctuations of the CMB, because the CMB is only kind of sensitive to very much radiation-like species. So, for example, it's not really sensitive to cold dark matter perturbations. But cannibal in this regime behaves almost like cold dark matter when it's concerned with the CMB, but almost like warm dark matter when it's concerned with the power spectrum. So this is kind of the trick of the cannibalistic dark matter. So here I show, for example, a suppression of the power spectrum. You can see here a warm dark matter model and the cannibal dark matter model in blue and orange. And they basically look exactly the same. But what is the nice thing is that the cannibal dark matter model will have no kind of impact on the CMB, while the hot dark matter model, in this case, some very high temperature warm dark matter model, will have a strong impact on the CMB. So this is shown in this plot. I just quickly flash it, where the green line and the green dotted line directly on top of it correspond to lambda CDM and cannibal dark matter, and the dot dashed line, which is slightly less luminous, is the hot dark matter line. And you can see that the hot dark matter completely spoils the CMB, while the cannibal dark matter does not. And this is kind of the trick of evading the CMB constraints. So you have this kind of delicate balance now for this cannibal dark matter between suppressing your power spectrum more and more if you increase this interaction rate, but also having possibly a larger impact on the CMB depending on how you also tune other parameters. So for example, we also included the fraction of all cold dark matter that is cannibalistic, or all dark matter that is cannibalistic versus cold. Okay. And thus you can have some possible CMB impact because you are still somewhat relativistic at this stage. And so if you increase your interaction rate too much, you might spoil some CMB constraints. And so now there's this balance between how much you suppress the power spectrum and how much impact you have on the CMB. This leads to exclusion limits like this one, where I show all the points basically that an MCMC, so Monte Carlo Markov chain, a sampler would get. And there's a lot of points, and these are colored by their corresponding value of S8, which is the clustering parameter sigma 8 times square root of omega m, basically. And you see that on the left-hand side, where the interaction is very low, the species basically behaves like cold dark matter. So the S8 is 0.85. You don't really care about it. On the right-hand side, the interaction gets stronger and stronger and stronger up until the point where you start to really influence the power spectrum. You start to really influence the S8. The points get a lot darker, but you also run eventually in the CMB constraints into this 95% confidence limit green band here. And so you can do this for any fraction, basically. For any fraction, you can play the same game. You start from low interaction rate, where it's basically like CDM, and then you go to higher interaction rates, and at some point you cross this magical threshold of interacting too much with the CMB. Now, this kind of line that you see here of the CMB, of course, means that for high fractions, even a low interaction rate is enough to spoil the CMB, while for very, very low fractions, of course, you need a huge interaction rate to actually spoil the CMB. So this is why there's this kind of degeneracy line for the CMB between the gamma 0 and F constraint. So the interaction rate and fraction constraint. Okay. And this you can, of course, translate also into like purely Bayesian plots. So here we show like 1 sigma and 2 sigma contour plots in the corresponding plane, not of gamma 0 and the fraction, but of gamma 0 and the corresponding S8 value. And you can see that kind of, if you take a super broad value, broad prior, sorry, you have a lot of regime where you basically recover the lambda CDM equivalent on top, the kind of green line. This is kind of where your interaction rate is very low. But if you go to higher and higher interaction rate, you start to slowly dip down into this kind of interesting regime where you are getting less and less compatible with Planck, but at the same time, and interestingly, you also start to suppress the power spectrum. And this is kind of the relevant region. So we actually did a couple of runs, one, for example, where we left the prior to be basically very broad, so it can explore all the region, but one where we also forced it to be in this kind of phenomenologically interesting region by setting the prior at a certain high interaction rate. Okay, and this Yudaki et al. 2020, just if you're wondering, this was basically one of the measurements of weak lensing that was given at the time. Okay. So finally, and hopefully quickly, I will summarize a bit of the spectral distortions that I also did work on. So currently we have, I think, released 2 papers. The third paper is in the release pipeline. So it's quite interesting. Spectral distortions in general is a tale of scattering of photons. So we have this kind of mini review of this paper here where I show the archive number. So if you want to look at this more precisely, you can look at this archive number and kind of find a lot more interesting details, and it's written like very pedagogically. Okay, so how does it work? Oh, there's a slide too much. Okay, so you start with the idea of having very efficient scattering. What happens if your scattering is very efficient? Well, your distribution gets a certain shape. From the law of kinetic equilibrium, you actually know that it has to be some, sorry, this is the correct slide after all. From the law of kinetic equilibrium, you know that it has to have a certain shape. And this is the shape I show here. This is a Bose-Einstein or Fermi-Dirac distribution. 1 over exponential of energy minus chemical potential over temperature, and then a plus minus 1. Now for the photon, you know it's a boson, and you know that it's relativistic. It doesn't have a rest mass, so you can kind of already narrow down the form a bit. So it's this momentum P minus the chemical potential over the temperature, then the exponential of it minus 1. Okay, let's see now what happens if you scatter very efficiently. If you scatter very efficiently, for example, with double Compton processes or Bremsstrahlung processes, you can actually create or destroy photons. So on the left-hand side, for example, I show a process where you actually create a photon. Now for the chemical potential, this is a disaster because in chemical equilibrium, if this process is really efficient, you have to balance the chemical potentials as well. So the chemical potential on the left-hand side is just an electron plus a photon. On the right-hand side, it's an electron and suddenly 2 photons. And so if you just write down the equation, you will notice that the chemical potential of the photon has to be 0 for this to be in chemical equilibrium. So if the scattering, for example, of double Compton scattering is very efficient, actually the photon chemical potential vanishes. And this is a form that I show above. Same for the Bremsstrahlung, where you have in the starting state 1 electron, 1 nucleus, and 1 photon, and in the final state you just have the electron and the nucleus. So again, the chemical potential has to be 0. However, as cosmic time progresses, these processes become more and more inefficient, the Bremsstrahlung and double Compton processes. So maybe there's only Compton scattering, so electrons and photons scattering of each other. So this would still enforce kinetic equilibrium. So we have the shape as we said before. Or maybe even the Compton scattering is getting super inefficient if we go to even later times. And then we can actually do expansion in like very small scattering interactions. So we start with some black body, and then you do a very tiny scattering, and you look at how is it distorted. And actually it turns out to be some very complicated shape. Okay, now let's reformulate all of these in terms of just black body, because we know that the CMB is actually very close to being a black body. So let's see how much each of them makes it deviate from the black body. So the first one is just a black body, so there's no deviation. The second one turns out to be a black body of a slightly modified temperature. We don't care about that. We measure the temperature today. We don't predict it. But also some tiny distortion, which is called a mu distortion. And finally, this very inefficient scattering also gets a name. It's called a Y distortion. So here we have the so-called spectral distortions of the CMB that we can generate just by certain processes not being super efficient. So for example, if Compton scattering is inefficient, we will generate a Y distortion. If Compton scattering is efficient but not Bremsstrahlung and double Compton, we get a mu distortion. So this is how they look like. The mu distortion is basically the green one, or M, and the red one is the Y distortion. We also show here a third distortion, which is a black body of a different temperature, but we don't care about this kind of temperature shift because it's not a true distortion. Okay. So when we inject energy into the thermal plasma, we can either efficiently rescatter it, getting no distortion, we can only Compton scatter it, getting a mu distortion, or we can only inefficiently Compton scatter it, getting a Y distortion. And this will depend on how far along in cosmological time we are, meaning how much energy do the electrons have, how many nuclei are there, is there charge neutrality in the universe from recombination, these kind of things. So actually, throughout cosmic history, you can do this kind of plot, and you see here that actually very early on, we generate only a shift in the black body. This is the blue curve, ignore it, we don't care. Then afterwards, we generate this green curve, which is this kind of mu distortion, which we really care about. At very late times, we generate the Y distortion. But please note, late times in the case of spectral distortions means even before recombination. So recombination is the left-hand side of this plot. This is the latest that we go. So we only care about the duration of the spectral distortions, of course, before the CMB decouples, before it's released, because afterwards, like, who cares what happens? Okay. So we have these two regimes at very high redshift. So Y distortions between 10 to the 3 and 10 to the 5, and mu distortions between 10 to the 4 and 10 to the 7. So this is very high redshift physics before recombination. And so we can probe actually stuff before recombination. So this is, for example, showing energy injection from annihilating dark matter. And this annihilating dark matter, if it has a lifetime that is short enough, it will actually significantly inject energy into the very early plasma where mu or Y distortions can be generated. And so this is where the green and the orange contour, which includes some futuristic spectral distortion missions, can actually observe a huge signal and thus put very tight constraints. So comparison, blue is the Planck plus the current spectral distortion experiment that we have, which is Virus. So Planck alone would just collapse here at like 10 to the 12 or so for the decay lifetime. But due to the Virus experiment, we get this kind of left-hand bump in the shape. And if we get more and more crazy experiments like Pixie or Prism, we can kind of improve the accuracy of this bump or the depth of this bump a lot more, thus constraining a lot more these kind of decaying dark matter models. But of course, we can also do it for a lot of other stuff. So we also in the paper show primordial black holes, or you can even do inflation. So how does it work? So it turns out there's a process called the dissipation of acoustic waves, which actually depends on an integral over the primordial power spectrum, damped by some damping scale. But since we're at very high redshift, this damping scale turns out to be very high. So we're talking about 10 to the 7 per megaparsec. So this is really like super, super, super tiny scales. But since we're at this early time, also lots of stuff is still homogeneous, even at these super tiny scales. There's not yet a lot of nonlinearity at this very early universe. Okay, which means that we can probe the primordial power spectrum even to very high wave numbers or very small scales, which means that we get kind of this independent probe from inflation. So let's now think about like crazy things, like let's do a model where we have basically the normal inflationary spectrum below some scale, and then we just modify the tilt above some scale. We just continue with a different tilt of the primordial inflationary spectrum. And we show here that we get different constraints. So the gray constraints, which you see are suspiciously absent here, they are from Planck alone. Indeed, Planck alone cannot put any constraint on this model. Planck's constraint is completely irrelevant because it would only probe at scales which are too well described by this normal power law. And the bend would be at higher scales. So Planck alone cannot put constraints. But we already have a Virus spectral distortion mission. So this is the red constraint, which kind of already excludes a nice chunk of parameter space. But with upcoming future spectral distortion missions, as like, for example, Pixie or Prism, you can get better and better constraints. I show on top of it 2 lines from like a previous paper by Jens Kluber et al., who did kind of the same analysis, but with like a lot more simplified assumption. And we actually showed that if you like really start to include a lot of the assumptions, you lose a lot of the constraining power, as you can see, comparing the black solid line compared to the blue line. Actually, you have to compare to the blue, not the orange. So the black versus the blue line, you can see that there's quite a lot of difference from correctly marginalizing of our intergalactic foregrounds and the kind of temperature shifts, and correctly taking into account Bayesian statistics and all of this kind of nice stuff. What you get as a final nice result, basically, is that you can then plot for the given parameter region that are still allowed the corresponding power spectra. And what you basically see is that around the Planck scales, the model is very tightly constrained. But as soon as you start to deviate from the Planck scales, these models usually can blow up quite a lot and become much higher or lower than the default power spectrum. And so this is exactly where the spectral distortions are relevant. At these scales of like 10 to the 4 per megaparsec, they are still constraining. And depending on how constraining they are, you get either the power spectrum like really diverging a lot, or only a bit, or only a tiny bit. Okay. And these are basically my research topics, and I would like to thank you for listening even so long. And I will just leave this slide open if you have any questions or comments.